Pretty nice, huh? Yeah, whatever.
That's nice. I don't like this angle. It's not 3D.
Better? Right, to answer your question, it's quite simple. The mid-semester test will be on everything. Simple.
Everything? Including the mechanics?
Including this, and what will come after this.
After?
Yeah.
Yeah, circumstance.
Everything
in here. Is it
that we've done.
Is it going to kind of going to fit?
Huh?
Per chapter. You know that.
What's wrong?
No. How many questions there?
I forget. About, I don't know. I don't remember.
Is there essays?
About 12 or something. What? Oh, your book's falling apart. I think Sylvia might have the plastic that you can slide down the side. I can go look at some time and see if I can get some. Okay. You've distracted me. The test will be on everything. Okay? Right, let's continue now. So next lesson, simple harmonic motion. This, like the circle lesson, is a big lesson. It will need 2, but I think we only have 1 lesson now, so we'll have to do half of this. Have you got that? Did you write it down?
Everything's still 1. Everything's still 1.
Until the day before the exam.
No.
Why?
I do it in computer.
We'll do it at a computer exam.
Oh.
It's a computer exam. It's even worse.
So we don't need counting. We can just use the test exam.
That's interesting, but I would still like you to come in. Thank you.
I take my snap.
I tell you what, you can come in and do the test in class and do it again at home.
Would you give us things like this so we can go?
No, you can still use pen and paper, of course. I just want you to type the answer into the computer, yeah. And I can collect up your paper afterwards.
Calculation or is theory?
No, it's all mostly calculation, but I have a couple of fill in the blank questions, like I have a definition and maybe I'll leave a word blank in it. You know, like, I don't know. Like, for example, maybe something like, force is the rate of change of blank with respect to blank. You know, so I'll just fill in the blank.
Test question?
What? Hang on, one question at a time. Yes?
Is the spelling important?
Is the test important?
Spelling.
Oh, is the spelling important?
Spelling. Oh.
As long as I can understand the word, it's okay. Yeah. So, as long as I can read that word and go, she means whatever, then it's fine.
Actually, we just put numbers.
For most of the questions, although some of them we have to type a word, like fill in the blank. Yeah. Okay.
Is it different time with 1 semester test?
Is it what?
Different time, semester 1, the end of semester.
Yeah, the questions are sort of just short questions. Like there's just like information, question, answer. It doesn't have parts to it. It's just story, question, type in the answer. I don't know. We'll talk about this in the next class. Okay, simple harmonic motion.
So you don't use it now?
I'm so busy.
Oh, okay.
I'm so
I
busy.
just want to know.
No, I don't have the test ready yet. It'll be ready, don't worry, for next week. It's okay.
Maybe you don't need to.
I know I will. I think Wednesday next week.
Do you know, next day, Thursday, it's really festival.
Is it? And what are you going to get me? I like books. I like coffee.
What do you want to get for me?
Get for you? I know. Right. No, you can talk about what you want to get me for Spring Festival later. Yeah, Spring Festival. But that's why I'm the teacher, you see. Alright, continuing now. So, this type of motion is a special type of motion called simple harmonic motion. And we see this motion a lot in physics. It's this kind of motion, it's this kind of back-forth motion. So in this example it's moving up and down, but let's think of other times we see this type of motion. So here is one example. Where else can we see motion that's kind of up, down like this? Or maybe left, right?
Parabola.
Which one?
Parabola, like the clock, the old clock.
Oh yeah, you have the right idea but the wrong word. Think again. Pendulum, that's it, yeah. So pendulum is swinging like this, yeah. From a clock. What else has motion like this or like this? Something bouncing. What?
Like the modeling. Like
The what?
it's moving. Like pendulum.
That's what she said.
Pendulum.
No, he's talking about Newton's cradle.
The Newton's cradle, yeah, it's the same thing with pendulum, yeah. Okay, so just like with circular motion, it's a special type of force that causes this motion. So you remember with the circular motion, the force that caused it was a force that acted towards the center of the circle and was perpendicular to the velocity. So what makes a simple harmonic motion? Well, this is one in which the force acts kind of towards the center as well. But the difference is this. The force gets bigger the further you are from the center. So, something is undergoing simple harmonic motion if there's a force which is proportional to the displacement. So that means if you pull it out further, you get more force. Not only is it proportional to the displacement, but it acts in the direction opposite to the displacement. So for example, if I pull the spring to the right, the force is acting to the left. So the force always tries to pull it back. And the bigger the distance, the more force you have. And it's always opposite your displacement. So because of that, we sometimes call it a restoring force. It tries to restore it, tries to take it back to the center. So if you think about if you had something stretchy, you pull it and let go, the force takes it back. Yeah. Key for the exam definition is they want to see the force is proportional to the displacement. Okay, that would be one mark. And then you get the other mark for saying it's opposite. So that's the 2 marks. Yeah. Okay. Got that? No. Who are we waiting for?
Me.
Okay. We'll wait for you, Bruce. We all like you. Oh, no, come on. Okay. Got that?
One more.
Yeah? Okay. Let's see. Come on, stuck. Just a sec.
We're waiting for you.
Yeah, I know. Okay, imagine a spring pulled out and then released. The velocity time graph would look as follows. So you have a spring, you pull it out, and you release it. So at the beginning, its velocity is 0. You pull it out, you hold it, 0. And then you let go, and what happens to the velocity? It gets faster and faster and faster, and then starts to slow and stop, and then reverses. So you might not be surprised to see that this is the graph. So at the beginning you pull it out and you let go. Why is it negative at the beginning?
From.
The
Yeah, it's heading in reverse. When you pull it out and let go, it heads backwards. So that's why it's negative. And then what happens here? What's happening at this time? It stopped. And then here now it's positive, so what's happening?
Reverse.
Yeah, it's reversed. So it's heading back to you now.
Yeah.
And then here, maximum speed, and then it starts to slow down, and right here is when it's back at the start of the motion, and it begins again. So this is the time velocity graph of the simple harmonic motion, and notice actually here, you see what I did there? It's not moving before the time is 0, that rest. Yeah? Yeah. Okay, can you draw this please as an example of what the velocity time graph would look like for simple harmonic motion?
Is it same with sine, correct?
Yeah, yeah. The way to make the sine one is if the spring is at rest and then you flick it and start it moving. So in this graph you've pulled it out and released. In the sine graph it's at rest and then you flick it to start it moving. Did you draw this, Bruce? Yeah? Where? Okay. Oh, okay. Continue? Okay, great. In simple harmonic motion we have terms which we also use in circular motion. So the ones that are in common are F, T and omega. And these mean the same thing. So what did F mean for circular motion? Frequency, and that's what it means here. The T? Time. So in this example the time will be the time for one cycle. Yeah? Except for the omega.
Omega is just the angle.
Yeah, but what angle?
According to speed, according to time.
Ah, yeah. But visually and physically, in the circle, the omega was how quickly the angle is changing.
Yeah.
Radians per second. So what could it mean for this one? The simple harmonic motion, which doesn't have an angle. How could it have an omega if it doesn't have an angle? Not quite. Any ideas? Has anyone seen this before? Still a type of speed, but it doesn't quite mean the same thing, since there's no angles. So if I tell you I have something here and it's moving in a simple harmonic motion back and forth, and I'll say the omega is 1 radian per second. Well, if it was a circular motion that would be easy. 1 radian per second would mean in 1 second it did this. So what does it mean to say this is moving at 1 radian a second when there's no angles? Any ideas?
100.
Yeah, but like, I suppose my question is 1 radian. Where's the radian? That's my question. Where are we measuring the angle?
180.
What? 180? What do you mean? You might be close. Go on. Yeah, but where was the 1 radian?
1 radian?
Yeah.
It's hard to express my thinking. Sorry.
Try!
Says like this.
Go on, yeah?
This is point.
Yeah.
This
Yeah. Yeah.
There's it.
Yeah.
This.
You might be close, but I'm not sure if you're...
1 radian.
Yeah, that's not 1 radian. That would be 3 radians. I think you're close, but let me show you. Well, you can use it for the graph, but I find this picture quite helpful. You see, when you look at this train, this wheel is moving in a circular motion, and this shaft here is moving in a simple harmonic motion. In fact, if I say this is moving at 1 radian per second, what I mean is if I actually could connect it to a wheel and cause the wheel to turn, the wheel would turn at 1 radian a second. That's one way to interpret it. There is another way. So my physics teacher back in high school, he had quite an older way of thinking about it. So this is a record player. Anybody's grandfather has this, a record player?
Yeah.
Yes, we know what this is, do we? The big record. And he said, imagine you put a candle on top of the record player. So there's a little flame here. And there's a wall here. And on the wall, you'll see the flame. And as this is turning around, you'll see this red dot move left and right. This motion here is simple harmonic motion, and this motion here is circular. And the relationship is the omega for this is the same as the omega for this. So if this was, we said, if this was omega of 1 radian per second, it would mean that this is turning at 1 radian per second. So, in other words, there is a relationship between the simple harmonic motion and the circular motion. There is a relationship. Which example is clearer, the record or the train?
Train.
Record.
You like the record one? You can visualize this, yeah? Yeah. So, continuing, there's an animation a bit like this online. If you wanted to, you can look this up later if you wanted to. But I'm sure you could type anything into Google, like animation, link between circular and simple harmonic motion. Yeah, I'm sure you'll find lots of animations. Okay, so, next. There's nothing really important to write here except just the interesting fact about the omega. So, terms we refer to. We have equilibrium or origin. What is this now? The origin. What could the origin be for this motion? What do we mean?
Is the start point?
Well, not necessarily. It sometimes is the start point, but not always
When
the start point.
forces equal 0?
That is true. But give me another definition that doesn't use forces, although that is true. Well, it's simply in the middle of the motion is where the origin would be. So like if it was moving like this, then the origin is just right in the middle. It's the center of the motion, that's all. What's the amplitude here? What's the amplitude here?
The distance away from the origin.
Yeah, the maximum distance. Yeah. Yeah? Continue. The next word, velocity. Well, we all know velocity. Angular frequency, we all know that now. Frequency, we all know. Time, we all know. And it's the same basic words.
How will we find the angular frequency?
Yeah, we have to look at the formulas now in a moment. Continue. Do you have all of this? Yeah? Okay. When the mass is at its maximum displacement, it's at rest. Therefore, it has no kinetic energy. So, if you think about the motion like this, out here and here, it's at rest. So what's the kinetic energy? 0 here and 0 here. That's fine. It has only potential energy. So it has potential here, and it has potential which is not 0 here as well. As it starts to move, what happens to the kinetic energy? Well, it will increase, and the potential energy becomes kinetic. So if you look here, as it starts to move here, what happens to the kinetic energy? It increases, but the potential energy then will decrease. In the middle, this is when it's going its fastest. So this is when the kinetic energy is its biggest. So this must be when we have no potential energy. Sorry, no potential energy. No, that's right. No potential energy. PE is 0. And KE is definitely not 0. And so on. So what I want to have a look at is the graph of what's happening here, of this situation, the energy graph. So what you have here is the X, and notice when the X gets bigger, the kinetic energy, which is this line here, gets smaller. And what is special about this point, when it has no kinetic energy? Yeah, where is this in the motion? Yeah, the maximum, isn't it? No kinetic energy. A lot of potential energy though. And as the ball is moving towards the center, you see it's getting faster, so the kinetic energy increases. And here we have maximum kinetic energy, but we have no maximum kinetic energy, but we have no potential energy. And then it's the same here, just on the other side of the origin. When we add potential and kinetic together, we get total. And why is total a flat line like this? What's the reason for this? Why, if I graph the total energy of the system, why is it a flat line?
KE plus PE equals always same.
Yeah, now don't say anything. What's the word for this? Shh. What did I say? I'm asking this dude. Yeah. No, there's conservation of energy. Conservation of energy is correct, but I just want you to say KE plus PE equals, and you said not change. What's the word for that? Do you know?
What's the question?
Question is, you said
Yeah.
KE plus PE equals not changing.
Yeah.
What is the word for not changing?
Conservation.
True, but it's smaller, simpler word.
Different?
Not too simple. In between these two. Yeah. Anyone know?
Always same.
But one word. Does anyone know what it is? Constant. So you would say KE plus PE is constant, correct. So the total energy is constant level. Yep. Now, sometimes they ask you to draw this graph in the exam. So just copy this down. There's one thing missing from the graph which I should really have on the graph. Right here and right here, what should I write? I should write minus A and plus A. Do you understand? Because that's the amplitudes. So that's here the X is A and here the X is minus A. So please add that to your graph. Confused? Questions?
What happens to the kinetic and potential when they touch each other?
Oh yeah, like what is so special in its motion when that's happening? I don't think there's anything special. It's just that part of the motion in which there's the same amount of kinetic and potential energy. I don't think there's anything visually special about that moment, you know. You'll notice the shape of the graph is what shape that you've done in maths class? That kind of looks like a sine and a cosine, but it's actually not. Quadratic, yeah. It's a quadratic.
Question.
Yes.
The beginning point is if the one side is minus A, other side is A, the meeting point is
Here?
no, that's
Here?
Where 1/2 A.
It could be 1/2 A, but I'm not sure. I feel like it is 1/2 A, or it could be 1/√2A. I don't know which. I'd have to calculate it. It's either going to be 1/2 A or 1/√2A because of the square, quadratic. But we can calculate it later.
Where we should write
Minus A, here. Plus A, here.
Yeah.
Here.
As the A increases, the kinetic decreases.
Well, the A doesn't increase, that's the amplitude. You mean the X?
Oh,
Yeah, when the X increases, like this, is that what you mean?
Yeah.
The kinetic decreases and the potential increases. Because it's getting slower as it moves out. Yeah?
Can you,
Oh, with my pen?
No, how to visualize the graph? Like in an example.
Yeah, so imagine actually literally that I had a spring here, and I pull the spring out, and I hold the spring right here on the x-axis. And I let go of the spring. What will the spring start to do? It will start to move towards the center. It'll get faster and faster. So if you were to measure its kinetic energy, it's increasing as the spring is moving towards the center. At this moment, it's moving its fastest, so it has the most kinetic energy. When it passes and the spring kind of flips around, the ball is heading away from me now, but the spring is pulling it back. So the kinetic energy is decreasing. And then what happens here? Well, it stopped. And then what will happen?
Go back.
Yeah. So it's just going back and forth like this. And you can plot the kinetic energy. You can measure it. So if you were to stop here, or not stop, but if you could freeze time here and ask what is the kinetic energy at this moment, it would be that. Yeah. The potential energy has an opposite relationship to the kinetic because the two together must be constant. So when the kinetic's high, the potential's low. When the potential is high, the kinetic's low, vice versa. Is it okay? Are you sure? So continue? Yes? Okay. So here's some the only thing I want you to know from this graphs is that not only does the velocity look like this shape, but if you actually look at the displacement and the acceleration, they're all this shape. They all have this sort of increase-decrease relationship. This will make sense now in a moment when we have a look at what the formulas are for these things. So, firstly, this formula is unchanged. T equals 1/f, that is still the same. Yeah? Next formula. That is also the same. T equals 2 pi over omega. Yeah? Okay. Next one. Now this is a new one. The acceleration is minus omega squared s. And you know what? Actually, let me just check your formula book. Sorry. There's a formula book at the back of your workbook, I think. Now, did they use X or S? If you like, guys, because in the formula book in the exam they use X, maybe you should change that S to an X, please, for displacement.
I think for X.
Yeah, use X instead of S, please.
Distance,
Distance, yeah.
So we have this formula
In the exam, yeah. Yeah. I should keep the letters the same, so it's actually an X.
Is provided
Yes.
on the weekend?
Yes.
Every weekend?
Except the one next week.
Except the one that's
Alright, fine, okay, you can use it next week, it's fine.
Okay, yeah.
Yes, every exam. Continue. Yep. So the next formula is, again, that should be x. And that's if you want to know the displacement. So, for example, if you, let's say you have something like, here's the origin. Here's the origin. And you have something which starts here, positive, negative, and it begins by moving to the right, very fast. And then what happens? Slows down, and then stops and heads back. Okay? If you have a motion like this, the formula for the x, how far it's travelled, is a, the amplitude, times sine omega t. Yeah? So, if you were to think about the graph, here is x and here is t. At the beginning, what's x? At the beginning, 0. And then what happens as the t increases? It increases. And here it's maximum, so it'll increase until it reaches a value of a. And then what happens after this? It decreases. So what's happened here? Back to the start, very good. But now it goes negative. What will that mean? Yeah, now it's actually on the other side here. Okay? So we use this formula if it starts, and this is important, if it starts from the equilibrium, if it starts in the middle and heads out to the positive. Okay? There's a different formula if it starts this way. There's the origin. If instead it starts here, but then heads left, again faster, 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 fastest, slower, 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 stop, and then turns around. This formula you would use x equals a cos omega t, again starting in the positive. So you see you have the two. Use sine if it starts in the middle, and cos if it starts at the ends. Yeah?
Is it possible to move the original here?
No, well, for us we keep the origin in the middle. Easiest for us to do. But yeah, these things can be moved always. Just like in the turning force question, we said we can put the origin anywhere, you know. It's convenient to put it in the middle. So, that's your next formula. So you use sine when it starts on the inside, and you use cos when it starts on the outside. How can you remember this?
Sine equals inside, cosine equals outside.
Yeah, now watch. What letter is in the middle of sine? What letter is in the middle of the word sine? I.
Original.
What letter is in the middle of the word cos? O. Inside, outside.
Oh.
Okay?
It's good.
It's very good.
Memorize.
Very good.
Inside.
I saw this once and now I remember it forever. I can't forget it. Yeah. Okay. Next. Guys. Next. Alright, what do you need to write down? Yeah, no, what do you need?
Sine is when it starts from the line.
From the inside. In the middle. Yeah, from the line.
And cos
If it starts on the end, the outside, and moves in.
So sine is like the pendulum, it starts from here.
Yeah, if you want to use the pendulum, the sine, did you say the sine or the cosine?
Sine.
The sine, yeah, it's like it starts from here,
And
and the cos is like it starts here. Okay, continue. Next formula. So next we'd want to know the velocity. And the velocity has an opposite relationship. So for the first one, the inside, you use a omega cos omega t. Otherwise you use minus sine. Now you might say, why have I got the minus here? Well, if you think about it, if you're starting on the outside here, if you're starting here, then what's the v, a positive or a negative? Well, it's a negative because it's heading left. So we need it to be a minus here. No? So far so good?
What is minus
Minus 1.
just minus.
What's the chapter A?
Amplitude.
Amplitude?
Maximum x. Yeah? Yeah. Like this.
The maximum point?
Yes, that's what I said. Okay, continue. Next formula. Again, that should be an x. So this is the same, the velocity. Except in these formulas you need to know the time. In this formula you just need to know the x. Yeah. Now, why is there a plus or minus? Well, because we don't know if it's heading left or right. You say you use the minus if it's left and the plus if it's going right. So one problem with this formula is it can't tell you the direction. You can only know the direction from these formulas. But this is good for finding the speed. You don't care about the direction. It's good for finding the speed. Yeah? Continue? No, yeah? Okay. Could this piece here, could this ever be negative?
No.
Why not?
It's not. It's important.
Yeah, but why can't it be negative?
If it can be negative,
Yeah, but why? Like, what is the reason it can't be this?
the leader is
No, that's why it shouldn't be negative. But why can't it be negative?
then the leader is be the image number.
The what?
Imagine number.
No, before that, what did you say?
If the inside
Yeah.
is the if EV negative,
Yes?
the leader
Yes?
it be the imagine number.
True, but now guys, please, you're English. English, please, listen carefully to my words, okay? I said, why can't it be negative? Everybody's telling me why it should not be negative. It should not be negative because there's a problem with the square root. I know. I'm not asking why it should not be negative. I'm asking why it can't be negative. Why it's impossible to be negative. You don't understand the difference. Yeah. I can't think of any other word. You're confused by my question, is it?
Is that sine WT or sine W times T?
Sine omega t, and the omega t is on the sine.
So the omega T is inside.
Is inside the sine, yeah. Yeah.
Times omega.
Okay, I'll give you an example. If I said, why can't children smoke? Well, they can't smoke because they can't buy cigarettes because they're not allowed to. Okay. If I said why children should not smoke? Well, they would get sick and it would be bad for them. There's a difference between should not and can't. So everybody's saying why this should not be negative because then you have a problem with the square root. But I'm asking why can't it be negative? Not quite. Yes.
And the chapter A
Yes.
is the maximum point.
Yes. Finally. Okay. So because of this, because I said the x is smaller than the a, if I asked you to do this, it can't be negative because this piece is smaller than this piece. It's never going to be bigger because if this was bigger than this, it would mean x fell outside. So it can't be negative because of this. Yeah? Can't versus should not.
Who's the winner?
Versus.
Yeah.
Right.
Who's the winner?
Who's the winner? No, it's not like one of those ones. Well, today, should not kept coming up, although I really wanted you to understand can't. Yeah? Right. Next one. The formula for the potential energy is a half m omega squared x squared. And of course, you already know the formula for kinetic energy. What's that? A half mv squared. And I think you said it earlier, the graph shape was quadratic. And you can see now why it's quadratic, because of the squares in the formula for PE and KE. Yeah? Who was that? Were you asking me about the KE equals PE? No?
PE equals PE.
Yeah, someone was asking me about what happens then.
Oh, yeah.
You were asking me what happens, and you were asking me if it was at A over 2. Yeah? So now you could calculate where it is, because you have the formulas. So you could calculate it. Yeah. Okay. We'll do just one more slide, and then we'll have to continue in the next class. So, in the real world, this is really what happens. Of course, you know that, because the spring won't continue forever. It doesn't do this forever. It actually will slow down and stop. And this effect, we call this dampen. Dampen the spring. Yeah, just like wet. It's another meaning for it. Again, in the exam, they could ask you to draw a graph to show what dampen is. Now, we don't, this motion, this damped motion, it's a very difficult motion. We wouldn't study it. You might study it at university. Okay, but the equations for the damped motion are much more difficult than the undamped motion. Who's doing physics next year?
Everyone.
Everyone? Not everyone.
Everyone?
Oh, who's doing physics next year? You're doing physics? Oh, you will definitely do this. Yes. Anybody else?
How do you know if I'm doing physics? How would I know? I'll check the
What are you studying?
maybe mechanical.
Oh yeah, they'll make you do a semester of physics. But it depends on maybe what you want to major in for how advanced the physics is. You'll definitely do this in your first year, for sure. And what are you studying next year?
Geophysics.
You might do it, but maybe not in your first year. And because with the geophysics, you know, you can think of situations of geophysics where there's a motion but it's slowing down. Yeah, like there's going to, but I think for the geophysics, probably more important would be fluid mechanics. You know, how liquids behave and gases and things like this. Okay, did you write that down and the picture as well? Yeah. Now this isn't actually a bad thing, this can be a good thing. I'll give you an example of using this in a good way. On the car, you know, the suspension, the spring on the car. This is a good example of damped motion, because when the car goes over the speed bump, okay, the car starts to bounce up and down, but what you really want is it to damp quickly. So if you think about a car going over a speed bump, you actually would want this to quickly stop vibrating. So it's not a bad thing. It's just, you know, it's just an effect in physics. Yeah. We will stop here because there's still a couple of more things to do, and then we have to look at some examples. Why is the colour blue different here and here? Dark blue, light blue, dark, light.
Almost same.
I know, but look.
Almost same. Oh, different.
See, these are the things I worry about. Yeah. Anyways, what do you think of the TV? Better than the projector?
Yeah.
Much easier to see? Looks nicer too.
How much?
And it has YouTube and Netflix. See?
Oh.
Netflix button. It has Wi-Fi. Huh? Well, if you want to give me your username and password, I can add it to the... No? Okay. We class tomorrow probably.
The Friday.
Tomorrow's Thursday morning. Yeah, we have class.
9 o'clock.
Is it 9 or is it 10?
9.
9
Are you sure?
Yeah.
I thought it was 10.
Yeah.
Oh, it's 10.
Ah, no. Isn't your day much better?
10.